The next speaker is Blaise. Nice to meet you, Blaise. I hope to see you in person. He's going to talk about the effective holography and zero sound for holographic matter. The stage is yours, Blaise. Go ahead.
Hi everyone. I'm trying to fix the webcam, which somehow looks very close up. Maybe not so bad. Alright, so slightly changed the talk to reflect its, the title of the talk to reflect its contents, but it's still going to be mostly based on this recent paper with Richard Davison and Eric methods. And I'll tell you a little bit about effective low temperature theories for holographic matter. So here are some further references that this talk is based on. So let's talk to the talk. So at finite temperature, we know that the low energy behavior of holographic states is well described by hydrodynamics. And hydrodynamics is an effective low energy description of the coarse-grained dynamics of interacting systems. By effective low energy, what I mean is that the degrees of freedom are no longer the full range of microscopic degrees of freedom, but instead only those that come out of the symmetries, the global symmetries of the system, the concept charges. And this is a low energy description because we focus on large distances and late times that are going to be much bigger than the local equilibration scales given by the thermalization length or the thermalization time. Do people don't see the PDF? Okay, then we'll continue. Now the dynamics of this concept charges is governed by the conservation equations. In particular, the time evolution of their densities is given by the flux of spatial currents out of fluid volumes. This construction, as I said, relies on local equilibrium, and the condition for that is that the time is large compared to the local equilibration time, and the length is large compared to the local equilibration length. What despite this is that then we can write constitutive relations for the spatial fluxes. So the spatial fluxes, they are not conserved. So they're fast operators, they decay in the bath of the conserved charges. And because of the local equilibrium condition, we can expand them order by order in gradients of the densities. This is a controlled expansion because each gradient term is weighted by the appropriate power of the equilibration length or equilibration time, such that L times grad is small. In the case of hydrodynamic diffusion, which is the example I was taking here, if you plug in the constitutive relation in the conservation equation, then take a Laplace transform and express the density fluctuation in terms of its initial value, then you can access the retarded Green's function for density, and that takes the usual diffusive form, with the presence of a diffusive pole in the denominator at omega equals minus I dq squared. And here we see the appearance of a diffusivity, which is related to the DC conductivity by Einstein relation, and also involves the static susceptibility K-N, which is simply the thermodynamic derivative of the density with respect to the chemical potential. This physics, it's well known that we can recover this by considering the closed Maxwell field in the background of a black brane with anti-de Sitter asymptotics, such as the Schwarzschild black brane. So here for simplicity, and I've written this in 3+1 bulk dimensions, but you could write it in any dimensions if you liked. And the properties of this holographic state are well known. In particular, we know how to compute the charge transport properties. We know that the static susceptibility is given by some integral over the whole spacetime of some ratio of metric elements and this affective gauge coupling Z. And it's the same coupling evaluated at the black body horizon that controls the DC conductivity. Going further, we can also consider the low energy excitations of the background itself, so planar Schwarzschild ADS, and that's governed by conformal hydrodynamics, which means that we have the conservation of the expectation value of the stress energy tensor. We can give this a gradient function, just like for the current. There's an ideal piece, which is the energy density plus the pressure times the fluid velocity mu. There's a term which is the pressure times the Minkowski metric A times mu. And then there's the viscous correction, which is the only one that exists for conformal hydrodynamics, which is the shear viscosity times the shear tensor, and the shear tensor is this transverse traceless combination of derivatives of the fluid velocity. If we look at the spectrum of collective excitations of the system, then we find two sound modes, which are over here with the sound velocity, which is the root of derivative of the pressure with respect to the energy. And then there's an attenuation that's governed by the viscosity, the viscous correction we have. This is for the longitudinal sector. And in the transverse sector, we simply have momentum diffusion, which is again controlled by the shear viscosity. This is at zero density. We can do the same exercise at non-zero density, turning on a chemical potential. And to this spectrum, we should add a mixed charge heat diffusion mode. That's exactly what we find in the Rice-Nordström asymptotically ADS black brane, for instance. So this construction, those effective theories, the emergence of this collective degrees of freedom, it relies on the separation of scales. We are always considering frequencies and wave numbers that are small compared to temperature. And what this does is it gives us a hierarchy of scales between the scale at which the hydrodynamic modes live, the small frequencies and wave numbers, and the scale at which all the non-hydrodynamic microscopic excitations live, which is usually over the temperature. Now you might want to ask, what happens if I take the limit of low temperature at non-zero chemical potential? This has been investigated in a number of papers in the past. We know that all this tower of non-hydrodynamic poles, all those poles that live at frequencies of low temperature, when the temperature goes to zero, they coalesce into branch cuts. But there's a bit of a surprise in that, in the case of Rice-Nordström, as you take the limit t goes to zero, then we see that gapless modes survive at zero temperature, which are the naive t to zero limits of the finite temperature hydrodynamic modes. This is a little strange because since you've taken t to zero, the zero temperature limit, you don't expect those hydrodynamic modes to persist to those low temperatures. Another surprise comes from considering so-called probe-brane setups, and there it's known that a zero sound mode appears. And by that I mean a propagating mode with a non-trivial velocity at zero temperature. And finally, a couple of years back with Richard Davison and Simon Jettel, we were looking at so-called Einstein-Maxwell-Dilaton theories, and there under certain circumstances you find that there is a long-lived excitation at low temperatures. So an excitation that is at frequencies that is much smaller than temperature. All of these features are not part of the conventional relativistic charge hydrodynamics that I reviewed on the previous slide. And so we'd like to understand then what is the effective field theory for those holographic states. For temperatures much smaller than chemical potential, either in the limit where frequencies and wave numbers are much smaller than t, or the opposite limit where t is the smallest scale in the system. And so I will take some steps in this talk towards answering that question. Actually, we know a few examples of zero temperature effective theories that give rise to gapless modes. The first example that I wanted to briefly mention is that of thermoliquids. This is the effective field theory that describes the low temperature dynamics of conventional metals. And in this case, the low energy fermionic quasi-particles stack up in momentum space due to power exclusion. And then we end up with a very large symmetry group, which tells us that the quasi-particle number is conserved at any point on the Fermi surface. People have called this a loop group. Now, by considering small perturbations about the Fermi surface, then it's well known that you find a zero-sound collective excitation at some velocity cs, which is less than the Fermi velocity, together with a branch-cut excitation at vfq. Again, vf is the Fermi velocity, and that provides, in this context, some kind of effective IR speed of light. But really, the presence of this collective excitation is now understood to be a manifestation or an anomaly of this loop group conservation. I don't want to enter too much in the details of this, but I will go more in details for the next example, which is that of superfluids, and we'll see pretty much the same kind of structure. So a superfluid phase of matter arises when a global Riemann symmetry is continuously broken, and then this gives rise to a gapless Goldstone mode. There's a very simple zero-temperature, low-energy effective field theory that one can write in terms of gradients of the Goldstone mode, which are equal phi. We see again the static charge susceptibility, chi and m. Now there's a new static susceptibility that multiplies the term, which is quadratic in gradients of phi. This is a superfluid density. Now it's immediate to see from looking at small perturbation of this Lagrangian that you find a spectrum which has a sound mode with a linear dispersion relation, and the speed squared is controlled by the ratio of the superfluid density to the charge static susceptibility. Now, within the context of this effective field theory, if you want to compute the attenuation, then you need to consider Goldstone-Goldstone interactions, and that would give you some power of q to the d plus 2, where d is the number of spatial dimensions. There's a useful way of rewriting this kind of dynamics in order to understand better where the collective mode is coming from. And that's by, in order to do this, what we do is we couple the system to an external gauge field through the usual term A bar mu J mu. Then this changes the partial derivatives into covariant derivatives in order to maintain gauge invariance. And here denoted by little a, the charge of the content operator. Then what you can do is consider the Hodge dual of the gauge covariant derivative in this, which I call K. The star K K itself is a D form in D plus 1 dimension. Now we want to write the conservation equation that this D form current obeys. And what we will do is we will use we'll make the assumption that there are no vortices, which means that phi is a smooth field, and so its partial derivatives commute. Then when we act with a derivative on star K, we see that the commutator du phi vanishes, but then the anti-symmetric dA term does not vanish, so that gives the field strength of our background gauge field. So that gives rise to an anomalous conservation log, d star K equals to minus A f bar. It has a mixed Hooft anomaly. It's an anomaly because it is proportional to some external source of the system, and it's mixed because the anomaly is proportional to the source of the global U1, not to the source of the symmetry associated with its deformed current. Actually, let me tell you what the symmetry corresponds to. This is a so-called d-1 form symmetry that tells us that the number of winding hyperplane of the phase of the Goldstone mode itself is conserved in the system. This is consistent with our assumption that there are no vortices around, so winding planes cannot be created or destroyed. This could only happen if we had vortices in the system. Let me say a couple more words about the difference between ordinary symmetries and higher form symmetries. An ordinary symmetry in this language is actually a zero-form symmetry. It gives rise to a one-form current. A one-form current counts particle excitations, and we count them by considering some volume that is dimension 0 manifold, and integrating over all of it and counting all the particles that you have. In contrast, a higher form symmetry, so here I'm taking the example of a two-form symmetry in 3 plus 1 dimensions. That's precisely the superfluid case that we saw for a 3 plus 1 dimensional superfluid. So a two-form symmetry counts two-dimensional objects and gives us a free-form current. It has this anomalous conservation law. It counts planes, so those winding planes that I was talking about. Now let me turn to holographic matter. I want to consider a specific kind of phase. Here, what I want to do is deform a holographic CFT in the ultraviolet by some relevant scalar operator phi in the bulk. So that in the bulk, that's a scalar field. It has some coupling to the Maxwell term, Z of phi, and some potential V of phi. UV is where phi vanishes, and there are such that have an asymptotic blue ADS space-time. Whereas what I want to have is that in the infrared, this scalar field phi has a runaway behavior. So what I'll do, for the sake of analytical control, is put scalar couplings such that when phi is large, V of phi and Z of phi are exponential of phi with some parameters delta and gamma. Now, when we solve the effective equations in this infrared region where the scalar field is very large, what we find are so-called hyperscaling violating scaling solutions. You can see that those scaling solutions are conformal to ADS spacetimes, and the conformality is controlled by a parameter which I call theta, which is the hyperscaling violating point. So now those metrics in the infrared are no longer scale invariant, they're scale covariant. That means that there's a non-trivial scale that doesn't decouple in the infrared. This is manifest in the behavior of the scalar field, since this is a logarithm. Yeah, I have the nice feature, as far as condensed matter applications are concerned, that there's a vanishing ground state entropy at low temperatures. Then what I want to do right now is to consider a probe Maxwell field in this background of UV ADS and infrared with non-trivial hyperscaling violation. This, you remember, in the beginning of the talk, this is where we saw simple charge diffusion. So again, the properties of charge transport are the same as before. For the static susceptibility, KNN, and the DC conductivity, they're controlled by parameters of those states. Then we turn on perturbations with small frequency and wave numbers. We expect charge diffusion exactly like before. And in particular, if we compute the AC conductivity, which is the zero wave vector limit of the current retarded Green's function, then we expect that there is no non-trivial frequency dependence at low frequencies in the hydrodynamic equation. So this is the expectation that when we go through the computation, assuming that the coupling has this kind of form, z to the delta chi minus 1, and taking delta z to be negative, then the static susceptibility goes to some constant. The DC conductivity diverges at low temperatures, so we have conductors, we're describing conducting phases, metallic phases if you like. Then when we compute the AC conductivity, we get a surprise. We find some non-trivial frequency dependence in the form of a Julia-like peak, which means that we have a peak centered at zero frequency and of a width gamma, which is 1 over tau, where tau is some timescale that's governed by this delta chi. This is a sharp Julia-like peak. It's telling us that there is a very long-lived collective excitation at low temperatures. And this is really not part at all of charge diffusion. So we'd like to understand why. Going further, if we turn on the wave number, then we see that there's a pole collision between this gapped pole that I was just mentioning and the diffusion pole. When this collision occurs, at some non-zero value of the wave number, this produces a propagating mode, which is precisely an example of this holographic zero sign that I was mentioning in the introduction. And so the goal now is to obtain the effective field theory of this collective excitation. To do so, we split the bulk action into a UV piece between the boundary, which is at r equals 0, and some cutoff hypersurface at r star, and an infrared piece between the horizon and r star. We solve the t and x components of the Maxwell equations, but we don't solve the r components, so the action that we get is only partially on shell. We plug those solutions back in the bulk action, integrated on the radial direction, and we find the effective boundary action, SUV, and SIR. So in there, I've defined various things, various objects. There's A bar, which is the boundary external gauge field, so the boundary source. There's little a, which is an emergent gauge field, which is simply the value of the bulk gauge field evaluated at the cutoff hypersurface. And then there's a scalar field phi, which is the bulk Wilson line, is the integral of the R component of the gauge field between 0 and the cutoff hypersurface R star. This produces an effective action which is very much like that of a superfluid. Compare it with the one, remember the one from a couple slides back. The difference is the coupling to this emergent gauge field little a. And in fact, in order to resolve the dynamics of this little a, we need to compute the infrared action. And when we do that, we find a kinetic term, which is just the field strength squared, which is pretty much the usual. But there's a big difference with ordinary electromagnetism, because now the gauge coupling is non-local. It has this frequency dependence. So the effective theory we get is the action for an emergent Gaussian like mode phi coupled to an emergent gauge field little a with a non-local kinetic term. Now what we do is we integrate out little a in this total action, and we find the currents of the theory. JT is pretty much like what you would get for a superfluid, but JI is very different. It has a non-local piece. We can now look at two frequency regimes. Either omega is much less, the frequency is much less than chi jj 1 over sigma dc. So that means we can neglect the second term in the denominator of JI, and then we have the diffusive hyper regime. On the other hand, if the frequency is larger than chi jj divided by sigma dc, then the second term wins, and the expression for JI looks more like that of a superfluid. In fact, if you plug the dispersion relations for the nodes that are produced by this kind of effective theory, and you plot them on top of the exact numerical results, so on this plot these are the black dots and black squares, you see that the exact numerical results are extremely well captured by this effective theory for temperatures that are not too small. This tells us that at zero temperature we need to do something slightly different. We can recast those results into the language of emergent higher-form symmetries. Again, start from the constitutive relation for JI that we produced, then multiply by the denominator on the left and on the right, rearrange that equation, and you see that you can recast this constitutive relation as a dynamical equation for JI with the emergence of a Hooft anomaly. Again, you can define a star k, which is d phi minus a bar mu plus little a, and find out that this higher form current obeys an anomalous equation with a mixed Hooft anomaly f bar with the global U1 symmetry, and a relaxation term little f, which is coming from the dynamical gauge field, and this is what produces for us the long-lived excitation. This is a little bit different from a superfluid because here the relaxation is algebraic in powers of temperature, so it's gapless, whereas for a superfluid the vortices are gapped. Now at zero temperature we can do the same calculation again in order to resolve what's going on there, and we find an action which looks pretty similar for the UV part. The infrared part is a little different. Now we have still have a non-local emergent kinetic term, but the gauge coupling has a slightly different form. And in particular, you see that it has a branch cut at omega equals CIR times Q, where CIR is the effective speed of light in the infrared of the spacetime. So the collective, the low energy spectrum here is a collective mode, the zero sound mode, CSQ, and the branch cut excitation. The branch cut produces this anomalous attenuation, which again is very different from the zero temperature superfluid. Let me now briefly say what happens at finite density. At finite temperature, we can construct states with an emergent Lorentz invariance and non-zero hyperscaling violation. And we saw that these contain collective excitations that are very similar to zero density. In that case, they reflect the dynamics of the incoherent combination of the current and the momentum. that is the part of the current that does not drag any momentum. And similarly to the finite temperature zero density case, we can recast them as an anomalous weakly broken conservation law for some emergent higher form current. But there's a big difference at non-zero density in that the static susceptibilities for the incoherent current and the incoherent charge go to zero as temperature goes to zero. So in fact, the propagating mode dissolves into a branch cut at zero temperature, which suggests that in this case there's a slightly different CFT. And I conclude with some future perspective, which is to try and understand the zero temperature gapless modes of spacetimes with infrared ADS2, and whether they can be understood similarly, and what the relation is to the Schwarzschild action. Thanks for listening to the talk, and I'll be happy to answer any of your questions. I see that there's one in the chat, and yes, that's correct. The EFT for programs is the same as the zero density EFT that I just described. So it can be understood exactly along the same lines as an emergent anomalous higher form symmetries, which is weakly broken by some emergent V-field in the infrared.
Okay, very good. Thanks, Blaise, for your nice talk. Thanks. Okay, let me see if there's any question. We have a few minutes. I don't see any questions here. But as I asked for the prop brains, do you expect any conformal field theory at zero temperature for this case? Yeah, do you expect any ADS?
Again, for the prop brain, do I expect what?
At IR regime, I mean any CFT?
So in fact here, the fact that it's a that it's conformal to some CFT doesn't really play a role. In the prop brain case, you could there's a paper by Andy Lucas and Chen that whether the effective hydrodynamic equation defines a relaxation of the current precisely of the same form as I described. They don't do the effective the EFT calculation, but if you do, the EFT calculation proceeds along the same line as we do. So you will again be able to understand the relaxation of the current in terms of decoupling to an emergent.
At the end, the dispersion relation looks like a K-gap equation, I guess. I see.
Wow.
Okay,
yeah,
thanks.
If you want to call it this way.
Thank you. I don't see any other question. Then we thank Blaise again. Be good. I invite the next